Okay, so the definition of this chordless cycle, these things are fine, right?
Mm.
Simplicial vertex, I think those definitions are fine. So let us see the statement of the lemma once again. So it says that so for every vertex x in a chordal graph G, there is a simplicial vertex of G among the vertices that is the farthest from x in G, right?
Mm.
Fine,
Yeah, yeah, it's okay.
right. So uh, we started with induction. So we are proving with induction,
Mm.
and n equals to 1, that is fine. And for n greater than equals to 2, we did the first case where if x is adjacent to all vertices, all other vertices, then we can apply the induction hypothesis over the chordal graph G minus x, right?
Mm.
So and then it follows, right? Now the case when x is not adjacent to all the vertices. So then how to do? So otherwise, so let us take T be the set of vertices in G with maximum distance from x, right? So we can collect all those vertices, right?
Mm.
So we can collect all the vertices that is at maximum distance from x, and we let h to be the component of gt, that is a subgraph induced by this set of vertices.
Mm.
Okay, be a, so it be a, it's be a component of this g of t, right? And we define another set of vertices. Let s be the set of vertices in g minus t having neighbors in v of h,
Mm.
and let q be the component of g minus s containing this vertex x. So this is how we are breaking the graph.
Mm.
Okay,
Mm. Mm. Yeah, yeah. Mm.
right. So now the our claim is this s will be a clique. So this s will be a clique, and what is our h? So h is a component of g of t, right? So we'll
Mm.
show that s is a clique. So that is our claim. So how to prove that? Now each vertex of x s. So each vertex of s has a neighbor in v of h, right? Because that is how we are defining. So S is the set of vertices having neighbors in V of H, right? So each vertex has a neighbor in V of H, right?
Mm.
And also it has a neighbor in Q, because Q is the component of G minus X that contains X.
Mm. Mm.
And a neighbor in Q. Now, if we consider distinct vertices from S, so for distinct vertices. Suppose U and V that belongs to S. So the union of the shortest UV path through this H and through Q is a cycle of length at least 4.
mm.
Okay,
Yeah, yeah.
right. So
Mm.
now, so what is happening is, okay.
This is
So
good.
this
Mm.
Q is there at this cycle of length as it goes. Now,
Mm.
since there are no edges from vertex of H to
Mm.
vertex of Q, so these are disjoint and there is no edge.
Mm.
So this cycle has no chord other than UV.
Mm.
So
Mm.
since G is a chordless, G has no chordless cycle, so U has to be so U and V are adjacent. So since no chordless cycle, U is adjacent to V, and since we have taken any two random vertices from S, we have proved that any two vertex they are adjacent. So this implies that S has to be a clique.
Mm. Mm. It's
Okay.
good. Very good. Yeah. Mm. Is it good? Oh, yeah, yeah, yeah. Mm.
Right.
What is the lead UV? Right. Mm.
Okay. Let me draw a picture that will be clear.
Mm.
So you have two sets. First of all, so you have this is your set S. This is your H. Okay. So now here you have taken two vertices. So suppose this is U and this is V, right? And
Mm.
using two vertices here, we are considering a cycle of length 4, at least 4, like this. And it is going and it is connecting to this chosen vertex X, and it is
Mm.
connecting like this. So it need not be direct edge, but some edge is there, right?
Mm.
And here is the this set of this is the T. This set is T, where T is the collection of all vertices, so which is farthest from, that is we have taken, right? So T is the set of vertices that is the maximum distance from X,
Mm.
right? And H is a component of GT, so that is fine. So this up to this is fine, right?
Mm.
This is T. Not here, right? Okay. So S is a clique, we have proved. So now what we'll define? So we'll define one more thing. So this is G prime. So what we are defining G prime to be? So let G prime be. So this is the graph induced by S union the vertices of S H. So this does not contain x, and hence it is a smaller graph than the original graph, right? So x does not belongs to G prime. So this implies G prime is a smaller graph than G, right? Now we can apply induction hypothesis to G prime and take a vertex u belongs to S, right? So because the induction hypothesis we are applying on the number of vertices, right? Apply the induction hypothesis to G prime and a vertex u belongs to S. Now since S is a clique, so we have that in S minus u, it is a subset of the neighbor of u, right? Because u is adjacent to all vertices in X, right? So other than u, all the elements of S is belongs to the neighbor of u, right? So now whether so G prime is a clique or not, it thus has a simplicial vertex. It has a simplicial vertex Z belongs to vertex of H, right? So since
Yeah, yeah.
the neighbor of Z is a subset of the vertex of G prime because it is belongs to G prime, so it is a simplicial vertex of G also. The vertex Z is also a simplicial vertex of G prime, right? And Z is a vertex with maximum distance from X, and hence we have achieved that particular vertex, which is a simplicial vertex. And Z maximum distance from X as desired. Okay.
Surprise or not?
Because Z we are choosing from vertex of H, right? And H is a component in so S is the vertices. So H is a component in G of T, where T is the set of vertices in G that is a maximum distance, right? So that's why this Z is the Z satisfies the condition. So it is a vertex with maximum distance from X as well as it is a simplicial vertex.
Yeah, yeah.
So this is what actually we wanted to prove. So we wanted to prove that for every vertex X, we will find a simplicial vertex that is among the farthest from X.
Yeah, yeah.
Fine.
Yeah, yeah.
Okay. So the next theorem is
Wait me a minute. I will write
yes.
down.
You want to go back? See.
Yeah, it's okay now. Sorry.
Right. So the next theorem is due to Dirac.
Ah,
Okay. So the statement is, so a
damn it.
simple graph has a simplicial elimination ordering.
Hmm.
So it actually characterizes which graph have a simplicial elimination ordering or not. So simplicial ordering, if and only if it is chordal. So if the graph is chordal, then you can say that it is a simplicial. It has a simplicial elimination order. So the statement is fine, right?
Hmm.
Right.
Yeah, yeah. Hmm.
Okay. So let us see the proof. So two directions, that if and only if. So first we'll assume that the graph has a simplicial elimination ordering and show that it is chordal. So this direction. So let G be a graph with a simplicial elimination ordering. Right.
Hmm.
Now let us consider. So you have to show that it is chordal. So what is the definition of chordal? So chordal is,
Kudo. Hmm.
yes. So a graph is chordal if it has no chordless cycle, right? So you have to take any cycle of length at least 4 and show that it has a chord, right?
Hmm. Hmm. Hmm.
Fine.
Yeah, yeah.
Right.
Symbol and no. Hmm.
Yes, it is simple and has no chordless cycle, right?
Hmm.
Okay, so that is what we are going to do. So we are taking. So let us take a cycle. So let C be a cycle in G of length at least 4. So now at this point, so when we have an elimination ordering, so at the point when the elimination ordering, so it is actually an ordering of the vertices in some order, right? So when in this elimination ordering, when it deletes a first vertex, right? So it has to delete a first vertex, right, from C. First deletes a vertex of C, say U or V, right?
Hmm.
So since it is a elimination ordering, and suppose V is the first vertex of this cycle C that is deleted in this ordering, then by definition it has to be the remaining neighbors of V must form a clique, right? By definition of the simplicial elimination ordering, right? So the remaining neighbors of V form a clique, right?
Hmm.
So the thing is, the clique includes the neighbors of V or neighbors of V on C also, right? So what is happening is, so suppose you have a cycle like this, right? And so suppose this is your vertex V, right?
Hmm.
So suppose it has two neighbors
Hmm.
like this. Suppose X and Y, right?
Hmm.
Now since V is the first vertex in the elimination ordering that is deleting from the cycle, so now X and Y and other suppose other neighbors are somewhere else, suppose. So this, at
Mm.
least these two neighbors are there. So since it is from a clique, so there should be an edge between x and y, right?
Mm.
Right. So since x and y belongs to
Mm.
this neighbor of v, right?
Mm. Mm.
And v is the first vertex. So v is the first vertex that appears on that ordering, right?
Mm. First,
So so that is important. So that is so this line is important, that v is the first vertex.
V is first vertex.
First vertex. So so we are given a simplicial elimination ordering, right? So there must be an ordering among the vertices which we are deleting gradually, right?
Ah.
So v is the first vertex on the cycle that we are deleting.
Mm.
Okay. So
Yeah.
is it fine?
It's okay.
Right. So x and y must be adjacent, right?
Mm. Yeah.
So x is adjacent to y. So this implies that this cycle has a chord, right? Because x and y are adjacent, right?
Mm.
So this implies the cycle C has a chord.
Mm.
So we have shown that any cycle which is length at least 4, it has a chordlet. So hence
Mm.
G has no chordless cycle. And this implies that G is chordal. Fine.
Mm.
So this is one direction. So we have assumed that the graph has a simplicial elimination ordering and proved that G is chordal. Now the opposite thing. So we have to prove that we have started with a chordal graph. We have to prove that it has a simplicial elimination ordering, right?
Mm.
So that is the opposite direction. So let G be a chordal graph, right? So now actually we'll use the help of the previous lemma. So the previous lemma what we proved is on this one, right? So for every vertex x in a chordal graph, so there is a simplicial vertex among the furthest vertex of x, right?
Mm.
So we'll use this property. So G is a chordal graph. So by the previous lemma, uh, every chordal graph have has a simplicial vertex, right? Fine.
Yeah, it's okay.
Right. So now we will choose like this. So this yields a simplicial elimination ordering. Ordering by applying induction on it.
Mm.
So since every induced subgraph of a chordal graph is chordal. Okay.
Mm.
So this gives me a simplicial elimination ordering, and we have this theorem. So every simple graph has a simplicial elimination ordering if and only if it is chordal.
Mm. Yeah, yeah,
Right?
yeah, yeah, yeah.
Okay.
Mm. It's okay. Mm.
Okay, so omega of h, I think we defined to be the clique number, right?
Click
That
number.
omega of g, we have defined it.
Click number.
The largest clique that is inside, right?
You mean click number?
Yes,
Hmm?
clique number of a graph we defined it. Omega of g something, some sort of that.
Oh my god. The number of click graph in given graph is right. Or what?
Yes, so the highest size of the clique that is available. Okay, let me write down. So this omega of g, so this is called the clique number of g. So this is the size of the maximum clique, maximum size
Maximum size.
in g. So what is the largest clique or maximal clique that is that can be possible
Mm.
or that is inside the graph g?
Uh,
So the number of
uh,
vertices is the clique number, right?
the number of vertices in the maximum click.
Right, right,
Yeah.
right.
Uh, yeah, yeah. So we face two problem. There is how many clicks graph in the given graph and what's the maximum click?
Yes. So for example, if we take an example, suppose you have maybe some sort of graph like this, right? So then what will be the clique number? What is the largest clique possible in this graph?
Four.
Right. So this our this thing is a clique, right? So this is a K4.
Mm, mm,
So this is the largest or the maximum clique that is as a induced subgraph I have, right?
mm.
So the clique number of this graph will be 4, right?
Yeah, yeah.
Right. So the next definition is actually includes that. Okay. So the next definition is, so a graph G is perfect. So the definition is for perfect if the chromatic number of H is equals to the clique number of H for every
Mm,
induced subgraph H subset of G. So this is actually a strong statement. So we'll say that a graph is perfect if
mm,
this chromatic number of H is actually equals to the clique number of H for every induced subgraph of
mm.
G.
Yeah,
Or
induce graph.
equivalently,
The induce graph include the grid or not?
the induced subgraph, yes, yes, we have to, yes, that is, in general, we don't know, but from the
Mm,
graph, it is possible, if it is possible that the induced subgraph always, if you take a induced subgraph, it has the chromatic number is actually equals to the highest size of the clique that is inside that edge, then we'll say the graph is perfect. It should hold for every induced subgraph of G.
mm,
So equivalently, what you can say is the chromatic number of GA induced subgroup by A. So it is equals to the clique number of GA, where A is a subset of.
Mm.
the vertex set for all such subsets.
Okay, 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 got it. Mm.
Fine.
Yeah, yeah, yeah.
Okay. So next we define the clique cover number, something called clique cover number. So the clique cover number, so that is denoted by theta of g of a graph G, is the minimum number of cliques in G
Mm.
needed to cover this whole vertex set of G. That is the clique cover number. So minimum number of cliques that is needed to cover the whole vertex set. Or
Mm.
one can observe that, so this theta of G is nothing but the chromatic number of the complement G bar.
Is the minimum number of clicks in C need to cover VZ?
Right.
Yeah, we can do an example.
Yes, yes. Example we will see. So the next example is, for example, if you have okay. Yes. So then you have, suppose these things are there, and the graph is, you have like this is your whole graph, right?
Mm.
So this is a whole graph. So the question is how many cliques are there we need to cover all the vertices. So that will give you the minimum number of cliques that is required to cover the whole vertex set. So here,
Mm.
if I take this K4, right, then then all these four vertices will get covered, right?
Mm.
So next, suppose I take this K3. So this is a K3, right? This is
Mm.
a K4, right?
Yeah, yeah.
And suppose I take this as one more. So this is K2.
Uh,
So if I take these three clicks, then all the vertices are covered, right?
uh, yeah.
So here the theta of G is 3.
Three click.
Yes, 3 clicks are equal. So I think this is the minimum one, and this will give you the click thing, then a click
Mm.
cover number.
Mm, mm.
Fine.
Mm, yeah, yeah, yeah.
Okay. Okay. So there is a theorem that is, okay. Let me write down. So there is a theorem that is well known. So let me state the theorem. So the theorem states that, uh, so it is called the perfect graph theorem. The statement is a graph G is perfect if and only if its complement that is G bar, is perfect. Okay. So you can say a graph is perfect even only if the complement is perfect. So we'll actually need some more conditions. So we'll prove this one later. So just to see an application. So how to
I,
characterize perfect graphs.
mm,
Okay, fine.
yeah, yeah, yeah.
Okay, so the next definition is, so the something called hereditary. What is hereditary? So a family of graphs G is hereditary if every induced subgraph of a graph G is also a graph in G. So suppose you have a family of graphs, right? So we'll say that is hereditary if every induced subgraph I take of a particular graph, that should also be a part of the class or the family of graph.
Mm.
Okay.
Family graph is also a graph in the family graph with hereditary.
So family of graph means there is a collection of graphs you are taking, right?
Mm. Not one graph.
No, not one. A family of graph means you are taking a collection or a group of graphs. So we'll say that they are hereditary. So if I take any particular graph from that class or the family, and if I take any induced subgraph, that must be also in that class.
Oh.
Right. So maybe an example will be, a simple
Yeah,
example is,
yeah, yeah. Symbol is best.
right. So suppose if I take, this is the biggest graph if I take, right. So this is a cycle, 4 cycle. Then what are the possible subgraphs or induced subgraphs we have? So we can have a path of, right. Maybe we can draw it better. Right. So this is a subgraph of the original graph, right.
Mm. Two common.
So if I take only this part, so this is, I have drawn like this open.
Mm.
So I can take also, if I take two vertices, suppose if I take this one and this one, right. If I take these three vertices, then I have this, right. I also have the
Mm.
single edge also I have, right. And I
Mm.
also have isolated edge. So
Mm.
everything should belong to this family, so
Mm.
that I can take any graph. If I take, all the induced subgraph should be also there,
Mm. 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 Yeah,
right.
yeah, yeah.
So for example, if I take this and this, then the induced subgraph is only two isolated vertices. So that should be also there, two isolated vertices. So like that, you have to form this collection.
Yeah, 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 yeah.
Okay.
Mm.
So one example of this hereditary is bipartite graph. So bipartite graphs actually form an hereditary class. So if I take the collection, hereditary class, and the chromatic number of G is equal to the clique number of G for every bipartite graph, right? Because the chromatic number of a bipartite graph is 2, right?
Mm.
And if I consider, so there are exactly two partitions, right?
Mm.
So since the graph is bipartite, so suppose this is X, this is Y, so these are the two partitions. So if I consider the clique of size this whole X and another clique of size this whole Y, then I cover the whole set of vertices, right?
Mm.
So the clique number or this number, the W of G is 2, or omega of G is 2. Also the chromatic number is also 2, right? So
Mm.
this implies that every bipartite, so bipartite graphs are perfect, right?
Mm. Bavatai. Bavatai graph. Mm. Mm.
Fine.
Two. Mm. Yeah, yeah. Chi
Okay.
is two. W is maximum clit.
Yes, yes. We can just have two clicks to cover all the vertices, right? Because I
Number
can
of
take a
maximum clit.
maximum size click to cover X and another to cover Y,
Yeah, yeah.
right?
Mm.
Okay. So the next theorem is
Mm.
so chordal graphs. So these are also perfect. So let us see the proof. So it says that so if I delete a certain vertices, so deleting vertices cannot create chordless cycles, right?
Mm.
So the family is hereditary. So if I take the family of chordal graphs, the family is hereditary. So now we have to only prove that the chromatic number of G is actually equals to the clique number. So we need only to prove that the chromatic number of G is equals to the clique number when G is chordal, right?
Mm.
So we have already showed in a previous theorem that if G is chordal, it has a simplicial elimination ordering, right?
Yeah, yeah, yeah.
Right.
Yes,
So since G is chordal, G has a simplicial elimination ordering,
mm.
right?
Yes, yes, yes. Mm.
So let V1, V2 up to Vn, so be the ordering, be the reverse of such ordering. Now we know that by the definition of this simplicial elimination ordering, so for each I, the neighbors of vi in this v1 to vi minus 1. So this forms a clique, right? Right.
Mm, mm.
So we'll apply greedy coloring on this property.
Oh.
So if vi receives the color k, so then the colors 1 to up to k minus 1. So this has already been used, right? So
Mm.
it appear on the earlier neighbors of vi, right? So if vi receives the color k, then already from 1 to up to k minus
Mm.
1, these colors have been used up, right?
Yeah.
So since they form a clique, so with vi we have a clique of size k. So
Mm.
hence we obtain a clique whose size is actually equal to the number of colors used, right?
Mm, mm. Yeah.
So hence our the clique number is equal to the chromatic number,
Mm.
and this is what exactly is needed to prove that it is perfect, right? So that's why the chordal graphs are perfect. So here, what I was saying is, so here also the clique number is 2 because the maximum clique that you can have is an edge, right? Because there is no adjacency here and no adjacency here, right?
Mm.
But what I was saying in the complement, I can cover it this as a whole clique, and in the complement I can cover with this whole clique. So the clique number is 2 here, and that
Yeah.
is same as the chromatic number.
Mm.
So here also we proved that same idea. So we
Yeah.
proved that
Mm. Mm.
chromatic number, right?
Yeah, yeah. It's okay.
Okay. So today maybe we'll stop here.